we shall learn about the Biot-Savart law in magnetostatics. We know that the current that is flowing through a conductor creates an associated magnetic field. The Biot-Savart law, which is considered to be the cornerstone of magnetostatics, allows us to understand and predict the magnetic fields generated by various current configurations like a straight wire, loop, solenoid, etc. The law relates the magnetic field to magnitude, direction, length, and proximity of currents. Let us now consider a loop which is carrying a current. The loop is assumed to be having an arbitrary shape. We now consider a very small element having length dl. So dl is a source point, and we want to calculate the magnetic field at a point with position vector r. So this point is the field point, and the distance between the source and field points are represented by the vector script r. Then the magnetic field at point P, due to a steady current that is flowing through the conductor, is given by the Biot-Savart law, and it mathematically reads as B, which is measured at position vector r. This is equal to mu 0 over 4 pi, then integral I cross r hat divided by script r square, then dl. This integration is along the current path in the direction of the flow, and dl gives us the length of the current carrying element along the wire. And as mentioned earlier, script r is the vector from the source to the point r. Mu 0 is the permeability of free space, which is given by 4 pi times 10 raised to minus 7 Newton per ampere square. And therefore the magnetic field, the unit of the magnetic field is Newton per ampere meter, which we denote as Tesla. The magnetic field Br, this can be written as mu 0 over 4 pi, then integral I dl hat cross r hat, because I is along the direction of dl, then over script r square multiplied by dl. Taking the current out, since it is a steady current, we assume that it is constant. So this is mu 0 I divided by 4 pi, then integral dl hat cross script r over r square, and therefore the Biot-Savart law can also be written as Br equal to mu 0 over 4 pi I, then integral dl cross r divided by r square. So this law can also be written in this form. We shall now do this problem. Find the magnetic field at distance s from a long straight wire carrying a steady current I. So this is illustrated in this figure. We have a wire which is carrying a current I. P is a point at a distance s from the wire. Now we are asked to find out the magnetic field at a distance s from this long straight wire. According to the Biot-Savart law, B is mu 0 over 4 pi times I, then integral dl cross r hat over script r square. So in order to proceed with this equation, we need to find out dl cross script r and 1 over script r square. So if we can find these terms, then we can substitute in this equation to find out the magnetic field at a distance s from this current carrying conductor. Now, the modulus of dl cross script r, this is equal to modulus of vector dl, then modulus of script r, then sine alpha, where alpha is this angle, which is the angle that the separation vector script r makes with the direction of the current carrying conductor, or the direction of the current. Now, when we inspect this figure, this angle is theta and this angle will be 90 minus theta. Therefore, this equation is modulus of dl, then modulus of script r, sine of pi minus pi by 2 plus theta. So that is equal to dl cos theta. Now in this equation dl is unknown. We want to find out dl. So let us take this distance as L. In that case, we'll have L as S tan theta, from where we'll get dl as equal to S sec square theta d theta, and this is equal to S over cos square theta d theta. We'll take this as equation number 1 and dl this as equation number 2. So with 1 and 2 we can calculate dl cross r. Now we have to find 1 over script r square. For that, let us consider the same triangle and then write S as equal to r cos theta, from where we can write 1 over script r square. This is equal to cos square theta divided by s square. Equation number 3. With that, the Biot-Savart law reads B as equal to mu 0 I divided by 4 pi, then integral s over cos square theta, then d theta multiplied by cos theta, and then cos square theta over s square. S and s square will cancel, then cos square theta and cos square theta will get cancelled. That is equal to mu 0 I over 4 pi s integral cos theta d theta. To proceed further, we have to find out the integration limits. We shall proceed by defining the limits for this integral. For that, let us consider this figure. So we have a wire segment having length dl, whose starting point is this and the end point is this. From point P, we drop a perpendicular which meets at this point. Now we'll take theta 1 as the angle that the starting point of the wire segment having length dl makes with a perpendicular drawn from the point P to the wire. Similarly, theta 2 is the angle that the end point of the wire segment makes with respect to the perpendicular that is drawn from point P to the straight wire. Now we have B equal to mu 0 I by 4 pi s integral theta 1 to theta 2 cos theta d theta, and this is equal to mu 0 I over 4 pi s, then sin theta from theta 1 to theta 2, and that is equal to mu 0 I over 4 pi s sine theta 2 minus sine theta 1. This gives us the field of any straight segment of wire in terms of the initial and final angles theta 1 and theta 2. And we may be curious to know what would be the magnetic field that is produced by a wire which is extended to plus infinity and minus infinity. So let us assume that this is the point P and this is the perpendicular that is drawn to the wire. Now as the length of the wire is extended towards negative infinity and positive infinity, so this will be angle theta 1 and this will be angle theta 2. That is, theta 1 tend to be negative pi by 2 and theta 2 tend to be plus pi by 2. In that case, the magnetic field is mu 0 I over 4 pi s, then sine of pi by 2 minus sine of negative pi by 2 which is equal to mu 0 I divided by 4 pi s, then 1 minus minus 1, and that is equal to mu 0 I over 2 pi s. So this is the equation for a magnetic field that is produced by a wire having infinite length. That is B equal to mu 0 I over 2 pi s. Note that the magnetic field is inversely proportional to the distance from the wire, just like the electric field of an infinite line charge. Now, what would be the direction of the magnetic field? According to the right hand thumb rule, the magnetic field would encircle the current carrying conductor in the xy plane, so that the direction of magnetic field would be along the phi hat direction, that is the increasing direction of phi. We shall now try to find out the force of attraction between two long parallel wires which are at a distance of d apart. So this is schematically shown in this figure. Conductor 1 is carrying a current I1 and conductor 2 is carrying a current I2. They are separated by a distance d. The magnetic field that is experienced at the position where conductor 2 is located due to the current in conductor 1 is given by B1, which is equal to mu 0 I1 divided by 2 pi d. So this is that field, and at the point where conductor 2 is located, this magnetic field is along this direction, that is, that points into the page. Using the Lorentz force law, we can now calculate the magnitude of force directed towards conductor 1. So that is F, force due to magnetic field. This is equal to modulus I2 then integral dl cross B, and this is equal to I2 then mu 0 I1 divided by 2 pi d integral dl. This is equal to mu 0 divided by 2 pi then I1 I2 divided by d multiplied by L. Now we can write the force per unit length as F equal to mu 0 by 2 pi I1 I2 divided by d. If we take the force due to the magnetic field of conductor 1 as F1 and that due to the conductor 2 as F2, then the magnitude of these forces will be equal. Let's now try to find out the direction of the force in two cases. Case 1 is where the two currents are parallel and along the same direction. If we assume this as the direction of current, the magnetic field due to conductor 1 points into the page, and that will be like this. And when we calculate I cross B, that will be directed along this direction, that is towards conductor 2. In the case of conductor 2, the current is along this direction, so that is I2, and the magnetic field is pointed outward, that is towards the viewer. And now when we calculate I cross B, which is a force due to the field B2, this will be pointed towards this direction. So F1 and F2 are equal in magnitude, but they are along the opposite direction. And therefore, parallel currents results in forces that attract the wires each other. Let's now consider the case where current I1 is along this direction and I2 is along the opposite direction. So I1 is along this direction and the magnetic field is pointed inward, and therefore that is represented as a cross. So this is B1, and now when we calculate I cross B1, this will be pointed along this direction, that is F1. For the second conductor, the current is in a direction opposite to that of I1. So I2 is opposite to I1. Now the magnetic field is pointed outward, that is in a plane perpendicular to the plane of the paper, towards the outward direction or towards the viewer. And when we calculate I2 cross B2, this will be along this direction. So that is F2. We see that F1 and F2 are along the same direction. That is, if the currents are anti-parallel, one up and one down, the force will be repulsive. We now have quantitatively accounted why two conductors which are carrying currents in the opposite directions repel each other, and why two conductors carrying currents along the same direction attract towards each other. We shall now find out the magnetic field at a distance z above the center of a circular loop of radius r, which carries a steady current I. The situation is shown in this figure. We have a loop having radius r, and we have assumed a current carrying element in blue arrow, and that element is represented by di. The field point is at a distance of z from the center of the loop, and the source point and the field point are separated by a distance script r as shown in this figure. And we want to find out the magnetic field that is produced by this circular loop. Now, if we consider a very small current carrying element, let us assume that it carries a current di. So in this case, the magnetic field will be circulating this current carrying loop. The direction of the magnetic field is given by the right hand thumb rule, and according to this convention, it will be in the clockwise direction as shown in this figure. At any point on the circle, the direction of the magnetic field will be tangential to the imaginary circle. So coming to the first figure, the magnetic field at the field point would be like this. It is represented by dB, And all such small dBs constituted by all the small current elements encircling the small loop add together to result in a cone. Now, what we'll do is that we'll resolve dB into a horizontal and a vertical component. The horizontal component is represented by dB horizontal and the vertical component is represented by dB vertical. Now every horizontal component gets cancelled because for every horizontal component there is an opposite component, and then these two vectorially add to get cancelled. Now we are only left with the vertical components, and all the vertical components add together to result in the resultant field. So which will be the magnetic field B, that is due to the circular coil. With this background, we'll try to solve this problem. The field dB attributable to the segment dl is dB equal to mu 0 divided by 4 pi times I, then dl cross script r divided by script r square. Now as before, our first aim will be to find out dl cross script r, and this is equal to mod of dl, then mod of script r, then sine of the angle between dl and r, as you can see in this figure, is pi by 2. So that is sine of pi by 2. This will be equal to dl because mod of unit vector script r will be equal to 1. And therefore, we'll get the magnetic field dB as equal to mu 0 over 4 pi, then I dl over script r square. Then as we integrate dl around the loop, dB sweeps out a cone. All the horizontal components of dB, that is dB horizontal, cancel, and we are left only with the vertical components. And all these vertical components will add together to result in the total field B. So dB along the z direction, this is equal to mu 0 over 4 pi I dl over script r square multiplied by cos theta. And this is the vertical component, that is dB vertical. The term cos theta comes because it is a vertical component. Now from the figure we can write cos theta as equal to r over script r, and that is equal to r over square root of z square plus r square. Therefore dB, a function of z, will be equal to mu 0 over 4 pi I dl over z square plus r square, then r over square root of z square plus r square, that is equal to mu 0 over 4 pi I multiplied by r divided by z square plus r square raised to 3 by 2 multiplied by dl. Therefore the total field B is equal to integral dB z, and that is equal to mu 0 over 4 pi, then I multiplied by r divided by z square plus r square raised to 3 by 2 multiplied by 2 pi r. 4 pi and 2 pi gets cancelled, resulting in B as equal to mu 0 I over 2, then r square over r square plus z square raised to 3 by 2. So this is the expression for the magnetic field that is generated by a circular coil having radius r. We assume that the field point is at a distance z from the center of the coil. Now we can restate the Biot-Savart law for surface and volume currents. For surface currents, it is Br equal to mu 0 over 4 pi integral Kr cross script r over script r square multiplied by dA dash, where K is the surface current density. And for volume currents, Biot-Savart law reads Br equal to mu 0 over 4 pi integral J cross script r over script r square d tau prime, where J is the volume current density. We have just found out the magnetic field due to a circular loop. If we have n such number of loops, then that particular entity is known as a solenoid. So a solenoid is a helical coil. We'll now try to find out the field, magnetic field that is produced by a solenoid. So the problem reads like this. Find the magnetic field at point P on the axis of a tightly wound solenoid that is a helical coil consisting of n turns per unit length wrapped around a cylindrical tube of radius A and carrying a current I. We have a cylinder having radius A and the cylinder is shown in yellow. And on top of that cylinder, we have a tightly wound solenoid having n turns per unit length. And that solenoid is carrying a current I. P is the field point. Now we have to find out the magnetic field at point P. For that, we'll start with the axial field due to a single ring. In the previous slide, we have seen that the axial field due to a single ring is mu 0 I over 2, then a square divided by a square plus z square raised to 3 by 2. We are given that n is the number of turns per unit length. Then in a very small length dz, there will be n multiplied by dz turns. Therefore, the magnetic field that is produced by n dz coils would be mu 0 I divided by 2, then a square divided by a square plus z square raised to 3 by 2 multiplied by n dz. So this is the magnetic field that is produced by n dz coils. And for a solenoid having n turns, the magnetic field will be integral of dB. And this is equal to integral n dz multiplied by mu 0 I over 2, then a square divided by a square plus z square raised to 3 by 2. And this is equal to mu 0 n I over 2, then integral a square divided by a square plus z square raised to 3 by 2 multiplied by dz. In the next step, we have to make proper substitution for dz and 1 over a square plus z square raised to 3 by 2. From the second figure, we have z equal to a cot theta. From where we'll get dz as equal to negative of a cosec square theta d theta, and that is equal to negative of a over sine square theta d theta. Also from the triangle, sine theta equal to a over a square plus z square raised to 3 by 2, and therefore sine cube theta equal to a cube over a square plus z square raised to 3 by 2. From where we'll get 1 over a square plus z square raised to 3 by 2 as equal to sine cube theta divided by a cube. Substituting 2 and 3 in 1, we have b as equal to mu 0 ni over 2 integral a square sine cube theta divided by a cube multiplied by minus a over sine square theta d theta. Sine cube theta and sine square theta will get cancelled. Then a square and a cube will get cancelled. Therefore, b is equal to negative of mu 0 ni over 2 integral sine theta d theta, and that is equal to mu 0 ni over 2 cos theta from limits theta 1 to theta 2. You can see that theta 1 is the angle of the vector that is drawn from the starting point of the coil, and theta 2 is the angle subtended by the vector drawn to the end of the coil. And therefore, the magnetic field is equal to mu 0 ni over 2 then cos of theta 2 minus cos of theta 1. So this is the equation for the magnetic field produced by a solenoid which is having a finite length, and the field point is assumed to be along the axis of a coil. Now we need to calculate the magnetic field due to an infinite solenoid. For an infinite solenoid, the field point will be somewhere like this. So that is theta 2 equal to 0 and theta 1 is equal to pi. Therefore, cos of theta 2 minus cos of theta 1 is equal to 1 minus minus 1, that is equal to 2, which gives us the field due to an infinite solenoid as equal to mu 0 ni.